Okay. I'll introduce the speaker today. So we have Dr. Gendreau. He is the principal investigator for the NICER, which is the Neutron, I think up there, but Neutron Star Material Composition Explorer. Mission of opportunity on the International Space Station. Keith has a PhD in physics from MIT. Just a little time ago, 1995, and for work with the X-ray detectors, CCDs on the OSCA, which is the Advanced Satellite for Cosmology and Astrophysics mission that we did with the Japanese. Since that time, he's working at NASA Goddard in the X-ray astrophysics branch, where he develops technologies for X-ray sources, optics, and detectors, as well as astrophysics mission concepts. He has a number of awards. He's received the Robert H. Goddard Award of Merit, the Rossi Prize in the High Energy Astrophysics Division, the Exceptional Scientific Achievement Medal, that's from NASA, the NASA Invention of the Year, and the John Lindsay Memorial Award for Space Science at Goddard, which is really Goddard. Yeah, Kristen knows one of Goddard's highest recognitions. So Keith, come on up and tell us all about NICER.
Thank you, Carl. Let me just say that NICER is a mission of opportunity that's been on the space station for over 8 years now, made by a lot of people. The picture doesn't capture everybody. There are people in this room who play really important roles in software, system engineering, all over the place. We reached across Goddard, and I think we made a really fantastic mission. It's really doing, I think, some of the most exciting science that's happening on the International Space Station right now. We have many more people that I don't have hard to get a picture of everybody. But as the mission evolved, different people came in and came out over time, but they all contributed responsibly. So NICER lives on the International Space Station. We have here to right. Started trying space station. There are big props that we will video later. We're on the outside, on the starboard side of the space station, where there's not a lot of activity, so we can actually do astrophysics there. We don't have visiting vehicles affecting us very much. Astronauts usually don't go out there. We can actually get away with a lot of things and do a lot of science in the time that we have out there. NICER, Neutron Star Interior Composition Explorer. Right now, we wrote a previous proposal because some of you who might have been involved in proposals before. The previous mission proposal was just nice. And it was not accepted. So the next round came around. We decided to play it. But there was another mission called NICE that was selected. It was an Earth space science experiment. So I thought it was us, but they read the acronym wrong. And so we made it NICER. We made it through. Paul Burt said he would force me to do it again and see if we would do nicest. Rolls off the tongue. I'll just show you how this looks. So we went up, kind of folded up, and then we deploy like you see here. We're basically a big empty box with. You'll see here X-ray telescopes on one side. We have these sunshades in front of them that keep them getting too hot or distorted, from the sunlight illuminating on them. At the other end of that big box, we have a bunch of detectors. We use commercial off-the-shelf detectors, and the reason we have 56 telescopes and not just one is X-ray telescopes want to be long and narrow, and if we wanted to have a large collecting area, it would have been a very long telescope, much longer than you could fit on the space station. And that box represents basically the maximum volume that they would give us. And so we filled it with as much as we could, made a science argument for a fraction of that area. And in the end, it was actually, for unintended reasons, having a lot of parallelism actually helped us quite a bit in terms of actually making the mission fit within cost. We had a couple of failures of detectors early on, and but we could show that that's part of a screening process, and that the redundancy actually made us stronger. It allowed us to look at the brightest X-ray sources and also the faintest X-ray sources. So we have a huge dynamic range and sensitivity, in part because of an unintended consequence of us having 56 small telescopes in this little box. There's a lot of things where we went up to the space station as an opportunity because it was low cost and whatnot, but in the end, we took advantage of the capabilities of the station to do way more than what we proposed for. And I hope to be able to touch on it as we go on. Underneath the box, there's a thing called a pointing wrist. It's actually a bunch of, it's 2 Type 5 actuators that you normally use on a solar array tracking mechanism. What we used it for is actually point our telescope at stars in the sky as the space station is going around the Earth, so we can keep track on these objects. We had our own star tracker that guided our flight software to make sure that we were pointing and tracking these things. All of our electronics was on the moving box. We're on a boom that kind of gets us extended above the space station so we can see the sky, right? And then we were attached to the space station and our launch vehicle by this thing called RAM, which is, I forget what the whole acronym stands for, but I learned a lot of acronyms on space. And it gave us a defined interface that allowed us to build things within cost, because we knew what we had to build to. There was less uncertainty. Our X-ray optics. I have one if you want to see one later on. This is what they look like. These are from Peter Solomitsos' shop, if you remember Peter. This is, I think, one of the last mirrors that he was actively involved in. These are thin foil optics, and since I kind of have a light source, you see they concentrate light down. If I could point my hand more steadily down to a point, we would put a detector at that point. We would use, like I said, I'll show you in a second, commercial off-the-shelf detectors. This is the picture of 56 of these telescopes mounted on the top of our optical bench, which we aligned in the high bay behind Building 5, Building 5A. We took that over, we put a collimator there, and we built this system to integrate this payload. Oops. So our detectors, I don't have one of our detectors with us, but they're about the size of my pinky here. They're off-the-shelf detectors from a company called Amtech. I'm sorry if I'm standing in your way. They're used for X-ray fluorescence analysis. So does this have gold in it, or is this, what kind of, what's the material composition of a sample? They weren't made for timing, and they weren't made for astrophysics. But what we did was we bought a bunch of them, and we shook them. We found that their standard processes that they use to make these things, they make about 4,000 or 5,000 of these a year. We needed about 56. We bought 100. Their standard processes were good enough that you could shake these things on a 3-axis at close to 30 Gs, and they were fine. Now, that's even with, you can kind of see it right here. This window here is very thin. It's silicon nitride, about 400 angstroms thick. It allows us to look at the very softest X-rays, but if a piece of dust falls on it, it breaks. Other than that, it can handle a lot of my time in integration is making sure it was very clean. But we lost only one of our detectors before launch from a piece of dust. All the rest were fine. We lost two of our detectors, and I'll show you in a second slide. this is the picture of the focal plane with all our detectors. And you see this harness mess that you see here. It's rather extensive. We had a couple tight radii, and we lost three detectors because the harness was too tight, and during our vibe test, things fatigued. But because we had so much redundancy in our system, we actually could continue with our mission. We actually flew 4 detectors that we knew were dead. We could have fixed them, but when you do the cost-benefit analysis, we found that we could still do our science without making that change. If we fought to make that change, I think we would have argued about little things. And so when you're doing it at sort of a management level, can we maintain schedule? And we did. So NICER actually, we delivered a month ahead of the schedule that we made in our step 1 proposal, and on budget because of decisions like this. So what does that telescope give us? It gives us basically order of magnitude improvement in capability compared to the last X-ray timing mission, the Rossi X-ray Timing Explorer RXTE that I think a number of you worked on. I don't have their effectively a graph here, but we basically had an order of magnitude better energy resolution. So when a photon comes in and we detect it, we can tell what its energy was to 2% as opposed to 15 or 20%. Our time resolution was, RXTE was about a microsecond. Ours is about 100 nanoseconds, an order of magnitude. Because we have optics and we can concentrate things down to a little dot, our sensitivity was much higher. And we worked to a lower energy bandpass than RXTE could achieve, and so it was new science and that we could read from that. And I'll show you some examples of that later. Our gimbal system allowed us to rapidly zoom, and I'll show you that in a second. I was just telling Frank Frischman that RXTE is the Rossi X-ray Timing Explorer, and that's Bruno Rossi, who was a professor at MIT and basically started X-ray astrophysics for us years ago. Well, when we delivered NICER, we put it in the back of a truck in the back of Building 5 and sent it down, but I wasn't going to let it go in a truck all the way down to Kennedy. I got in a car and followed it the whole way. And I got to meet the truck drivers, which were a father-son team named Ron and Ronnie Rossi. So they asked me what the name of this mission was. I said, well, it's NICER, and it's replacing this thing called the Rossi X-ray Timing Explorer. That's our name. So anyhow, true story. Interesting coincidence here. They drove carefully. So this is NICER moving on the space station once we've been deployed. All right, this is about 60 times real speed. And for most of the time, we're kind of staring at a star in the sky. But then something like a solar panel will get in our way. Some other part of the sky. And so the space station would give us a model of what the solar panels were going to do as a function of time, what the space station attitude was, and that type of stuff. And so we could make a plan that made the maximal use of time. So NICER's overall efficiency tracking celestial objects, which is what we care about, was about 85% of the time. 15% of the time we were slewing. This is fantastic. It allows us to do a lot of things. So a lot of our observations in one orbit, so in one orbit we might do between 3 and 6 observations of totally different targets. And because we could plan, and because we had this big actuator that had strength, and then when we're on top of a 1,000,000-kilogram platform, we could rapidly slew, and we could kind of walk and chew gum at the same time. We could look at a lot of different objects and do different science.
Is that an actual video?
That's actual videos. That's the other cool thing about Space Station, right? That I didn't appreciate before we got up there. They got tons of cameras up there, and there's 6. Right now they used to be this thing called the 6-pack. It's now like a 12-pack. They still call it the 6-pack, but it was now it's 12 video streams that are coming down. You know, some of them are high def, and they sometimes wonder what they're going to point the camera at. And they would look at us because we were kind of the big moving thing. So we had lots of good exposure on the space station and allowed us to actually see what's going on, which is, you know, for a lot of our missions, we never see them again, right? So this was kind of this is yeah, probably more. It's been a little while. Yeah, when it's dark, we don't see anything, so it's going to be a little less of a So that capability of being able to rapidly slew was one of NICER's really big major strengths, something, again, that we didn't propose in the original mission, but in the end, it became very powerful. What I'm showing here is 3 successive ISS orbits being with ground tracks across the Earth. And in the red bit, we were flying over Asia, right? And at that time, NICER was looking at a target called the Crab pulsar, right, which is a very famous X-ray astrophysical target. And we were doing that because there were radio telescopes in Japan that were also looking at it. And we wanted to have simultaneous time from our X-ray instrument, you know, to compare to the radio data, right? And then as we crossed like the northwest part of the U.S., we slew, and then we started looking at a totally different target, this thing GRS 1915+05. This is a black hole system, and it's a very interesting system. It has lots of weird variability, and what we did was we made that slew so we could look at it and have coordinated observations with an optical telescope in the Canary Islands at the same time. So in one orbit, we're doing multiple targets. We're providing X-ray data point to combine with other instruments on the ground and actually in space as well. And so, you know, over the past 8 years, we've done over 500 coordinated campaigns where somebody asked us if NICER look at this thing, and while we're looking at it to see if something is interesting, or we can compare it with the other multi-wavelength data that we have. We did it with things in low Earth orbit. We also did it with OSIRIS-REx, which was going out to an asteroid. They had a X-ray detector that was going to look at the sun. It was actually the same design X-ray detector as what we used for NICER. They wanted to calibrate that system, and so we did a coordinated observation with something going through an asteroid. You know, to calibrate that system. We also did a coordinated observation with the one lander, the most recent lander that had an X-ray telescope, landed on the moon, to do a calibration of that instrument as well. So simultaneous observation is made possible by the flexibility that we have on the space station. Can people hear me okay back there? So the other thing that was kind of different about NICER, most of our funding came from the Science Mission Directorate as part of the Explorer program. And at the time, the next mission like ours, for its Phase A study, was given $250,000 to do everything and prove that you were going to fit within your cost cap and your TRLs were high enough. Well, we had a deal with the Space Technology Mission Directorate, which I think it was the Office of the Chief Technologist at the point, where they're interested in using some of the targets that we wanted to look at, some of the neutron stars that we wanted to look at that are really good clocks. So a neutron star is something that's about 1.5 times the mass of the sun, but it's kind of squeezed into something that fits within the beltway, right? And some of them are spinning hundreds of times a second. And imagine if my nose is a hot spot that's emitting radiation. As I'm spinning around, you know, the spot in your field of view is coming in and out of view, and it's going to blink. And 1.5 times the mass of the sun spinning hundreds of times a second has a lot of angular momentum. So some of these pulsars are extremely good clocks. You know, some of them on year-long timescales are better than the best atomic clocks. And atomic clocks are the foundation of GPS. And so STMD wanted to see if we could do a demonstration or prove that it's possible that we use pulsars as natural infrastructure for a navigation system that would work, independent of the Earth and well beyond low Earth orbit, going to the outer planets. And so we did that as a software experiment on NICER. It was called Sextant, or Station Explorer for X-ray Timing and Navigation Technology. Another acronym, right? And what NICER would, what Sextant would do, that software would do, is it would kind of sniff the data that's coming out of NICER as we're looking at pulsars, and it would try to measure the pulse phase, so that we can get an idea of when the pulses arrived. If they were a little late or a little early, we would know how to adjust our navigation model of where the space station was using an extended Kalman filter. And so we did dedicated experiments at the beginning of the mission where we proved that we could, determine where space station was to about 7 kilometers on average, and we could maintain that for days as long as our experiment went. It took a few hours to kind of reach equilibrium, and 7 kilometers is not as good as GPS, but if you're at Pluto, you don't have a lot of options. And so this is kind of an interesting enabling technology for the future that STMD wanted to demonstrate, which we did. And STMD gave us a sizable amount of money, about 10 times what we got from the Explorer program, which allowed us to actually build the hardware, including optics that are, pretty high TRL, to make a convincing case in the SMD review panel, which got us in. But it was a challenge, right? I was asked to talk about management. I remember at our site visit, it was asked of me. So you have an SMD, board and an STMD board. Who do you answer to? Right? And because it's like 2 people. And unfortunately, our STMD boards, said, this is just a 6-digit WBS number to me. Just make this happen, right? And he was willing to work with SMD. It was a good partnership that way. And I think we demonstrated that we could make things like this work in a way that benefits everybody. This graph on the right is kind of a prediction of how something like NICER would do a stripped down version, just one telescope, on a trip out to Saturn, right? And in terms of position, 3D position resolution, and you can do basically about 10 kilometers or so, and you do better than Deep Space Network, Delta Door, 24 hours every 7 weeks type of view. So the idea that we were pitching to that part of NASA is that we could take the load off of DSM, which is pretty intense right now.
So with all the slewing around, did that affect the performance, or how did we?
So we slew and track. Slew and track. Our pointing system, the LSU was fantastic, right? So we weren't, and we got locked right in there, right? And so we, so short windows, right? But the extended Kalman filter magic that the navigation folks put into this made that enough, right? So low Earth orbit, something on space station in particular, is really challenging, right? Because not only is your window short because the Earth is there, because there's solar panels and all this type of stuff. So for an interplanetary trajectory, we should be able to do much better.
Right, that's what I was thinking.
Yeah. So now I'm going to talk about science a little bit. So SMD paid most of the bills, and indeed most of the work we did was science. So there are kind of 3 broad places. Legacy science, which is what we propose to do in our proposal, which is studying neutron stars and understanding how they work. Then there's this next level, which I call observatory, which wasn't in our proposal. There's a lot of things in emit X-rays, and so NICER spent a lot of time looking at things like black holes. We look at comets. We have observations of the Earth's atmosphere. We look at stars. We did lots of different things. I'm not going to be able to talk about all of them here, but I'm happy to talk about more details. But lots of very interesting things that we did that NICER's ability to kind of spend a little bit of time every orbit, combined with other observations and other wavebands, had a lot of good bang for the buck. I call it, oh man, I'll talk about this. Basically, we call it target of opportunity capabilities. Because we're very flexible, the sky, and because the sky is very dynamic, there are lots of people who go, hey, this thing just went kaboom over here on this star. Could you look at it? We had a system to handle target of opportunities and chase those things down. We automated it to a degree, and I'll talk about this in the system called OMAN, which gave us very rapid response. So our record for somebody calling us and saying, hey, there's this thing that we saw a transient on a ground-based optical telescope, we don't know what it is, to us looking at it, getting data, and getting it to the person, and then publishing it in not a peer-reviewed journal, but what we call the Astrophysics, the Astronomer's Telegrams, which is basically, because it's dynamic, you want to get the information out there quickly. It was like 3 hours from the request to the publication of what we learned. And that triggers all these other telescopes around the world and in orbit to follow up on it. So NICER was doing a public service in a sense. TDAM is time domain and multi-messenger astrophysics. Our ability to look at a lot of different things on different time scales feeds right into it. And I don't have a lot of time to talk about it, but you'll see some flavor of it in the next slide. We're going to talk about our legacy science, which is our level 1 requirement is to measure the radius of a neutron star. And like I said, a neutron star fits within the beltway, but exactly how much, right? How are we going to do that? Because our telescope, this telescope, even if I could hold this really well, the angular resolution is not particularly fantastic, right? And neutron stars are several parsecs away and a few kilometers across, and we're looking for hot spots that are maybe the size of neighborhoods. You can never resolve that, right? So how did we do it? The video stopped, but what happens is there are hot spots on neutron stars that emit radiation. And so here are 2 neutron stars, right? They're both the same radius, even though they don't appear to be the same radius. If you have a hot spot on it, on a star that's got low mass or somewhat bigger radius, what happens is, it's just like that, what I was telling you before. If the hot spot was on my nose and I turn around, when I'm looking this way, you don't see the hot spot, right? And so the pulse goes away. But if my head was super dense, right? Compact enough, it's possible that when my nose is over here, the gravity of my head bends the light around toward your view. And that changes the shape of a pulse, right? And so we collected tons of data of many megaseconds of data of several specific millisecond pulsars that spin with millisecond periods, and we stitched together all the data so that we could get a combined light curve that's very well defined. And then what we did was we bought a ton of supercomputer time, right, to actually do the gravitational light bending for different models. And we looked at different possible shapes for the hot spots. And we did this as a function of energy, because NICER has that capability. And we could use that to actually infer what the mass and radius ratio was for neutron stars. And if we have independent mass information, we get a really good measurement from radius. But it turns out in some of our isolated things, we can get both mass and radius to some degree as well. And we did this on a number of pulsars. This was the first 2 that we did, PSRJ 0030 and PSRJ 0740. These are just phone numbers for a couple of millisecond pulsars that we knew about. And they gave us mass and radius numbers that are interesting for nuclear physicists to understand the densest matter in the universe. One thing I want to point out is we had to kind of work out the shape. And if you look at TSRJ 0030 on the left, you see that one of those hot spots doesn't look round. It looks kind of stretched out. And in both cases, the hot spots are not kind of nicely oriented around the star. And the reason that is the magnetic field structure on the neutron star is very complex, and that's what leads to the heating that we see. So we learned about the magnetic field structure of these neutron stars. So this is some modeling based on our data of what the magnetic field structure looked like. It's very complex. And for those of you that were on the NICER team some time ago and participated in the, what is our, we voted for what the, you might remember this, Bruce, what's the best logo for our sticker? This is our sticker. And the picture, this thing right here is kind of a textbook model of what our neutron star, pulsar, was supposed to look like. It took us a little while because you saw our data. It was a little bit more complicated. One of our graduate students in Amsterdam, after we realized that it's more complicated, decided that we should change. Haven't made new sitting around to people, but that alone is very interesting, right? And that's not too bad for like an optic that can't really image, but yet it's giving us imaging information that the best telescopes that we could ever make can't produce. This is kind of a common theme when I talk about. So that data we can plot. The green and black curves are from the NICER results of this is mass versus radius. This is complicated. This is neutron star equation of state. Like, it's, how does pressure and mass play against each other in very dense systems? Neutron stars are denser than the nuclei of atoms, right? So it's very interesting nuclear physics start squeezing out, and they have these models, these kind of curvy things that nuclear physicists come up with. Is it possible you can break neutrons into quarks? Quarks become important. And NICER is kind of, our data so far has ruled out kind of the more exotic models like that. So you might have heard of strange stars, which are quark stars. Our data is not consistent with that. And so, astrophysics is helping the nuclear physicists here. We also, some of our neutron stars we look at have what are called type 1 bursts. So a neutron star, is near another star, and matter is falling into its gravity well and starting to kind of cool up on the surface of the neutron star. And every now and then, you build up enough critical density that it ignites in a thermonuclear explosion. And in a fraction of a second, there's explosion happens that pushes the ash cloud hundreds of kilometers off of the neutron star surface. It's very hot, and then it cools off, and then you can kind of see it in these plots here. This is intensity versus time. This is fraction of a second, and here is in a few seconds, the intensity has dropped. NICER also had spectroscopic capability, so we could look for emission and absorption features, spectral features, which would be gravitationally redshifted, which gives us independent measures of the mass and radius of neutron stars. And these are really cool because we would see these live on our HK data in Building 32. Like, you see, boom, right? You can see it's really one of my favorite times at Goddard was to be in looking at the real-time data and what the heck was that, right? Anyway, we have other methods, reflection spectroscopy. I don't want to spend too much time on this because it's a little complicated, but we can look at gravitational and Doppler broadening of emission lines near neutron stars, because as matter is flowing into the neutron star surface, parts of that flow is extremely fast, a large fraction of the speed of light. And so if you excite emission from a particular emission line, rather than appearing monoenergetic, it actually gets broadened because of the Doppler and gravitational redshift that are there. And we can use the shape of that line profile to infer what the gravitational situation looks like near that star. I want to transition now into black holes and get past this time. So as I said before, when you take a picture of most of our objects that we do in X-ray astrophysics, apart from supernova remnants, black holes, neutron stars, the actual data looks kind of like a dot, right? If you had an image. But you're all been told that black holes are a lot more interesting if you watch the movie Interstellar and if you look at some of the recent results with interferometry. It's a little bit more complicated. So how can we learn about things at the small spatial scale with something that's just a light bucket? And the idea is basically use our time resolution that we have to infer spatial distribution on the sky. So this is from Erin Parra. She was looking at a new transient that we had learned about when NICER was up called MaxCJ 1820. And what this is a picture of is a black hole. This is an artist's impression. Black hole. A black hole, just like a neutron star that's accreting matter, will have matter coming in an accretion disk that's kind of orbiting and then eventually falls into the black hole. And above this system, you have this this kind of bluish thing. This is called a corona. It's basically a hot gas. And what Erin Carr did with NICER data is she looked at the time series and energy. Oops. All right, so you see these little moving arrows? So those are photons that start from the corona, X-ray photons. They come down and they hit our accretion disk, and they excite fluorescence, and then those photons get detected by NICER or whatever, right? And again, this all looks like a point source for our best telescopes, but by looking at the delay time between the light blue and the dark blue arrows, we can infer a travel time of what those photons had to move, and infer what the structure looks like around this supermassive black hole. And in the case of MaxCJ 1820, with the data that we took, we could determine that the corona was bouncing back and forth at the level of 80 miles, right? Now, it's 10,000 light years away. So timing has effectively given us an angular resolution of a physical process around this black hole, which would be the equivalent of if you put a P on the surface of Pluto and took a picture of it from the Earth, right? That's the kind of angular resolution we're talking about. You would need to actually physically see this in a traditional telescope technique. So X-ray timing and we call reverberation mapping gives us that insight. We use this on a lot of our targets. This is an MIT graduate, Jim Yi, who used this to look at a ton of black hole binary systems, binary systems within our galaxy. And she's been learning systematically new interesting things about how those systems evolve with time. I won't get into it, but it uses this reverberation mapping technique. So these are black hole systems. The black holes are about the size of our sun in terms of mass, like the solar mass, but they're a black hole. There are black holes in other galaxies, and we tend to call them AGN for active galactic nuclei. And the ones that we see are typically much more. There's an AGN called Assassin 18EL, and it has some other names. It's about 1 million solar mass black hole. It's in another galaxy, which again, NICER, the whole mission was about looking at stuff within our galaxy. So we started this whole thing of looking at extragalactic targets, and because we had the flexibility to look at this thing at a fairly good cadence, we could look at it nearly every 90 minutes for 4.5 years and look at how it evolved with time. And Megan Masterson, an MIT graduate student working on this data, has written a few papers based on that. She's finished her thesis actually on this. And we have a number of objects like this that we've been able to look at. Another extragalactic transient that we've looked at has been these things called QPEs, quasi-periodic eruptions. So there are things in the sky that were not known before maybe 6 or 7 years ago. If you look in the sky, you might see, hey, something was bright for an hour or so. If you happen to look in that right direction at the right time, you might see it. And then if you go back and look at it the next day, it's not there. Well, there's a whole class of objects that seem to blink like this on time scales of hours to days or weeks. All right? And they're only in the very softest X-ray band outside of RXTE's capability. And NICER, with its capability to follow up on potential sources, we've discovered more than half of these things were quasi-periodic erupting sources. What we think they are solar mass style black holes with an accretion disk and a star nearby. I'm sorry, million solar mass type black holes with a kind of a sun-like star nearby that's flying around that black hole, and it's plunging in and out of the accretion disk, and it makes a little puff of hot gas that you see. And it's very soft. And what's interesting about these targets is that you might have heard of LISA, which is trying to detect, it's a new type of astrophysics where instead of light, we're going to use gravity, gravity waves. This is the kind of object that LISA, that class of object that LISA would be looking for. And so we're trying to find an electromagnetic counterpart to these types of things. And NICER's done really exceptional work because of its flexibility to look at a lot of different objects at the same, concurrently with each other to do very long time bursts. Next thing I want to talk about is another thing that we didn't propose when we put NICER together. This is using the ISS really as a multi-tool laboratory. So NICER was put on the starboard side of the space station. There was another experiment that was put on the space station by our Japanese friends called MAXI. It was put up years before NICER went up. And what MAXI is something that's very good at seeing things go boom in the night in X-rays, right? And it would, its sensitivity was fairly low, but it had a really wide field of view. So if something happened over there, right? And MAXI would find a lot of these new black holes that we were learning about that we did a lot of science with. But follow-up, rapid follow-up enables more capability and our understanding of what's going on. So what we did was in 2022, we implemented this new experiment where we used a laptop computer that was inside the space station running Windows, right? I still can't get this out of my mind. It's running Windows, and what we did was we put basically software to kind of sniff the internet on it to actually sniff the raw data coming out of MAXI. And then we worked with our Japanese colleagues to actually use their event detection software to look for transients. And if it found one, we would transmit that information using the ISS infrastructure to NICER, where we made a small flight software change, right, to, I'm looking at Bruce and Dan, who are aware of what we did in the days. And if, a certain flag was ticked, NICER would follow up on it automatically. And so we're combining two instruments that weren't meant to work together, right? Work together on the space station. And actually, I learned that there's the Japanese internet and the US internet on the space station. They're different, right? We crossed that boundary, right? We did a lot of things that they didn't think you could do, and it became a good story for space station that, again, so if you ever come to my lab, you'll see it's a mess, but you'll see there are a lot of tools around my lab. And when I want to do something, I usually use this tool and that tool, to do something that's better than what the individual tools could do on their own, and that's what we did here with the space station. they always argued that as a national laboratory, and this is a great example of using the tools in a kind of, I think, a cool way. And this is just a little cartoon in Max. You can see something on our OMAN computer, which is a Windows laptop. We would look for that data, and we would send that to NICER, to the ISS infrastructure, and then NICER could do a little raster scan, find it, and go, this is what I think it is, and collect data, and then we transmit that data to the world. We could do this in minutes from the time that Max was to when we actually had data, which was, I think, very fantastic. We expanded it a bit. We used the infrastructure we put in place to do automatic TOO response from the ground as well, because there are a lot of facilities on the ground and in space that communicate back to the ground to do automatic TOO follow-up. So 6 years into our mission, the downside of space station is there's a lot of stuff happening. Right? There's a lot of vehicles coming. We had gotten damaged a little bit. In front of our X-ray mirrors, I don't have it here, but there's these thin foils that we put to block optical light and for thermal reasons. And one day, a visiting vehicle came, and it took us a couple weeks to realize it because it was kind of subtle. But we had extra optical light noise in our measurements during orbit day. We, because there are cameras on space station, we could look at it and we could see that there were little tears and stuff. And so we told space station folks, we have a little issue, and we kind of came up with an idea that we could put like an eye patch over the broken bits and get rid of the optical light loading. And in fact, later on, I'll show you our sticker. We have it looks like a pirate sticker. We came up with a way to kind of patch these things, and Space Station agreed to actually help us. And so we worked with the robot team, and then the astronauts, the EVA people, also approached us because they were interested in it. And if we weren't on the space station, we wouldn't have either choice. And to my amazement, the EVA team, both of the teams seemed very positive about it, and we went down very deep routes in each of these. But the EVA team stood up to it and said, "We're going to do it." In 1 year and 1 day after we detected, or after the damage occurred, we had delivered our hardware to Johnson. And over that time, we trained 6 astronauts, Don Pettit, Nick Cave, Nina Cartman, a bunch of astronauts on how to do the repair. And going down to the neutral buoyancy lab down at Johnson. And in the end, we did this. So last January, this is a picture of Nick Cave taking a selfie. And you can, after the next picture, a little better. You can see kind of nicer reflected in this helmet, right? This is the first X-ray astrophysics experiment to be repaired in orbit. Apart from Hubble, the only telescope to be repaired in orbit by astronauts. So we did this with the coins between the couch, the cushions on our couch, and basically a lot of goodwill with the space station programs. We produce a lot of science for space station, and they recognized it by the time we came with this request. And I'll say that's also one of the coolest things that I've ever experienced was working with astronauts to do this type of thing. I've learned a few things if you want to talk about it before. There's getting things done, and then there's working with the astronauts to get things done. And, there's a parallel universe there. Unfortunately, about 6 months later, we had an issue with our gimbal actuators. The Type 5 actuators that we have are motors with a 200 to 1 harmonic drive, so that we could do the very fine pointing that we need to do. One of our actuators, an azimuth actuator, stopped being responsive over a certain angle range. And And so we think what's happened is the harmonic drive had worn teeth. We are nowhere near the nominal end of life for the saturator. We're about a third of the way into it, I would say. But we were using this actuator in a little different way than most people use it. We're looking at that star, and we have to turn a little bit this way, a little bit that way, a little bit this way. All those little steps, I think, did a little bit extra wear than the normal thing when you're traveling the sun and you're just constantly going in one direction. So that's what we think has happened, and we've stopped our science observations. And it kills me, right, because I was really enjoying this. We've done a lot, and some of you have heard me talk, maybe seen this slide before. NICER, I think, is the biggest producer of science papers of any experiment on the space station. The graph shows you an ISS product they put out every year about the science they do. And the green arrow shows you when NICER was launched, right? The red curves are space and Earth science, which includes NICER. And just for example, in 2022, NICER produced 61% of all the Earth and space science papers. We put out about 1 to 3 papers a week. Even now, we've been dead since January. The archive is incredibly rich, and we're still producing more papers than any other experiment. We have a science team that's fully engaged even now. We have guest observers who are still looking at their data. We have archival data analysis all going out, and people are doing science with that. This slide's a little old. We have more than 30 PhDs that have come out of NICER data, hundreds of students involved. I think this was my first mission as a PI, and I think for a lot of our leads, it was their first time as a lead for different things. And so it was a great growing experience for the engineers and scientists and students at Goddard and universities around the world. I'm kind of proud of that, and we're continuing that even though we're not working. The other thing I want to add is that the stuff that we learned from NICER, pulsar navigation, that's something that's starting to resurrect itself right now with the new Moon to Mars initiative. Pulsar navigation, I think, is something to consider to go forward, and STMD and other agencies are actually interested in this. There's a bill going through Congress called the Celestial Time Standardization Act, which is asking for a way to kind of get time for Tom and you need to set your clock in space everywhere for whatever reason. They wanted to have a way that you could set the clock independent of the Earth. And so some of these pulsars, like I said, are very good clocks. So a lot of the NICER data we've taken so far applies to this, and we think that we can keep doing this in a later mission that we're trying to do. So we're trying to get a kind of a pulsar navigation experiment going again. The X-ray source we used to calibrate this is something that won the Invention of the Year in 2019. It's a time-modulated X-ray source. You can take X-rays with arbitrary light curves over time, and so we work with NASA and the hospital to make a no-moving parts CAT scan machine that has the possibility of doing CAT scans with an order of magnitude less radiation dose. For example, we have a little rotating skeleton that's from a dagger hand at Mass General with an X-ray, with a CAT scan system we made using our X-ray source up there. And we're also working on applying NICER technology for handheld instruments for going to the moon to do elemental analysis, exploration. And I just want to say it's a small mission. We were only 55 million SME, which a few years ago kind of that's small these days. We had 15 million from STMD, but we did a lot. I think we produced a ton of science at the space station. We've been getting really good results at nuclear physicists that are not normal NASA followers. They're using that data. We have been demonstrating applications that are useful, and some of the technologies that we put together to build nice architecture have useful applications on the Earth. I've got some other slides on. I was told to talk about management and stuff at some point, and I can talk about that offline, or I can step through it now if you like.
Hey, Keith, why don't we go?
Huh?
Why don't we go to questions?
Questions?
Yeah.
Okay. I'm done. Thank So the question is, if we did that as a free flyer, how much would it cost? So at the time, so the prices were different. Maybe you could get a 3-axis bus for 25 to 40 million, I guess. I don't know. We wouldn't need our pointing system, right? Which is in our situation costs about 15 million. So we would need a downlink capability, ground stations, which that's going to be other bits of money. I think it would have cost more, right? We basically were kind of like the people that moved into the space station apartment and took over all the utilities. Right? We didn't pay for the solar panels, we didn't pay for a lot of things, so it would be a bit more for sure. Maybe some next level.
How much new software development was off the shelf?
So I'm going to point to these guys, but my recollection is it was like 80% code reuse or something. Right? It was 80% code reuse, and then we kind of customized a few things. The Goddard people have a model for how to build things, that are, with different instruments, and we build right into that. And we benefited from that. Now, the Windows software, I don't know, that's all.
Yeah, so the tip and cue example with Maxi, right? Where Maxi tipped off.
Yes.
How could you repurpose that for future, multi-mission TDAM work?
Yeah.
Is it being repurposed?
Yeah, no, I've been thinking about that. So if we were to do a free flyer again that has this type of capability, there's a school of thought that your mission should be fully contained, and so that kind of pushes you in a system engineering problem into, I think, a challenging environment. So we need an all-sky monitor and then a pointed instrument, and they might have very different thermal mechanical requirements and observational constraints. So I say that from experience because we were looking at doing this as an astrophysics probe. We wanted to have something that's very sensitive optical loading. Like if it's glued across the sun, it's all over. Right? Yeah. The beauty of nicer is you can stare at the sun. It's speculative for that kind of purpose, right? So what I would think about doing is not doing an all-sky. I would make a pointed instrument that does something very well. There's a lot more in the not too distant future, space internet using, say, Starlink, that type of stuff. Right? You can imagine, making use of other resources that give you the ASM equivalent. Not all of our ASM stuff is X-ray driven, right? So there's the Rubin Space Telescope that's coming online and seeing like 100,000 transients a night. And we would be overwhelmed with this type of stuff. So you almost want to have strong enough computers on the ground to figure out what you want to chase down and adapt that model over time. Right? So I would think about separating things because I think the comms are going to get better in the not too distant future. That's my first one. Yeah.
When you were talking about your observations of the neutron stars, You showed what the mass versus radius plot. And I was wondering, do you think you determined the maximum packing of mass to ratio for neutrons? I thought there was a theoretical limit. And I don't know whether or not you had the capability of saying anything about whether you were making observations close to the maximum packing.
So let me just start off with saying I'm not the best person to answer that, but you can see in this plot, there's this is these curves here and here are based on theory, right? And so this bit of curves assumes that there is a maximum force that the neutron stars are stiff. The neutrons are stiff; you can't break them, right? And this group of curves suggests that there are forces you can apply that causes the quarks to separate from each other, and that's a little bit more exotic, right? And so one of our big requirements was to see, could you rule out the exotic one or not? And so our data is consistent with the more traditional, the stiff nuclear theory. But some of the other measurements, there's this red and black curve. These are, the black curve here is that's from that was from the gravitational wave source that was detected a few years ago. The idea is you could look at the chirp and get some idea of the radius, the biggest radius it could be before it combines. And that doesn't give you as tight a constraint as NICER did. But you'll see that its constraint actually, covers both the stiff and soft constraints, while NICER's three measurements here are all consistent with stiff nuclear theory. Does that answer your question?
Thank you.
No.
Repeat the question.
So the question was, have I presented this to ICE or the U.S. administrator? And the answer is no. But I think there are things, there's lots of things you can like. Why do you want to look at neutron stars? How does that connect to going from the moon to the Mars and stuff? And I think there's lots of things out there that you don't really know, right? On the face of it, studying about neutron stars and ultra-dense matter and understanding whether the stiff nuclear theory is relevant or not. Why does that matter, right? But if you can show that along the way, the data you get gives you a capability which is, saves you money and time, to support the outer planet missions, that's a real possibility. Understanding strong gravity, why do we care about that? Well, that affects the shape of these pulses and when we do our analysis. All these things that don't seem like they're really connected with figuring out where you are. I look out the window when I'm driving down the road to see if I've gone past the Missouri Legion post or not. Well, in space, I look out the window and it's a little bit hard to see if I've gone past the window I need to be captured in Pluto orbit. Maybe this gives you that capability. So I think that's the kind of message that I think needs to get to people who don't see the importance of doing science. You don't really know. When we, like our X-ray source, just to kind of get back, we made an X-ray source modular. My intention was to simulate pulsars and do something for mission I call black hole imagery. But I knew, and sure enough, it happened that people out of the woodwork contact me like, hey, your X-ray source, could you use it to do this, this, and this? And I'm like, that's a cool idea. I never thought of that before, right? And so you don't know, right? You need to put the stuff out there and have a reason to listen to what's around you, and not presume what the applications are. So that's the message that I would give.
All right, Keith, thank you very much, and we'll be here afterwards to answer some more questions, or?
Yeah, I'll be around for a little bit.
Okay, good. Thanks.